Okay, we are picking up where we left off last time. We were talking about scalar line integrals, and remember the big idea was we were interested in domains that don't really fit very well into our previous constructions, right? So here we have, for example, a one-dimensional domain, but it lives in a two-dimensional world, and it just doesn't fit very well in stuff we've already constructed. So what did we do? We just made up a new idea for a Riemann sum. This is morally equivalent to what we've already done. It's just tailored for this scenario, right? But it remains that we're computing the whole as the sum of the parts, like every other integral we've ever done. It also remains that on each part, on each little piece, right, we're going to understand what's happening on that piece by looking at quantity per unit size times size. Again, exactly like we did with every other integral we've ever constructed. Here, size is a length, and so this thing that will become our integrand is to be thought of as stuff per unit length. Okay. All right, and this is about where we left off last time. Let's see. Well, I guess we also recognized this notation and this terminology, and I think that's about where we left off. Okay, so how to compute these things. Now, let's not lose sight of the fact that computing is not the only thing that we do, right? I mean, a really, really important aspect of understanding scalar line integrals is to realize what to do with them, right? When do you use them? And that's where this stuff that we were talking about up here kicks in. You know, the reason we need to understand this Riemann sum, it's not for computational purposes. It's so that when we encounter a problem, right, we encounter some sort of an application, we can talk about, oh, I can answer that question by breaking it up in this, you know, in a way kind of like this, which we shorthand like this, and thus get to something that I can then worry about how to compute, right? Making the connection to applications in the first place comes from Riemann sums, as I've soapbox speeched previously. Okay, so yeah, to computation. How do I compute? We have previously, in talking about change of variables, talked about the idea of having an undesirable domain. Now, I think I'd call that an undesirable domain. I don't even know what to do with it, right? It's dimensionally unrelatable in some sense. And viewing it as being an image of something. Right? Now, that's how we did change of variables. We take our undesirable domain, we find a way to view it as being an image. Oh, good news. That's just a parameterization in this case. Oh, lucky break, we already have the tool that we need to set this up for doing something kind of like a change of variables. And so what we have to figure out now is just how to do the pullback, right? How do I take an integral on this domain that I don't know what to do with, and how do I turn it into an integral on, let's say an integral on the t-axis, which I do know how to do. This is just single variable calculus over here. Okay. So, yeah. Super lucky, parameterization, something we already had in our toolbox, and that's exactly what we need to do this. The only thing that we have to figure out concerning the pullback is the stretching factor issue, right? So there's this thing that a little piece of the t-axis, its image is going to be a little piece of our curve. They're not going to be the same size, probably. Right? This is going to be a factor different from this. I need to know what that factor is. And how did we figure that out when we were doing change of variables? Well, we drew various vectors and, little parallelogram and figured out the area and, made some arguments about what the matrix looks like. And there was a whole thing there. And here's the good news. No such issue here, because dt just represents a certain amount of time. ds represents a certain distance. What's the relationship between distance and time? Speed. Distance is speed times time. So our stretching factor, it's kind of a freebie. The stretching factor is just the speed, namely the magnitude of the velocity. And so we're in business. This ds, that's part of our Riemann sum construction that we're taking accumulations over a curve and how do we represent that, etc. That ds, well, here it is. It's just x prime dt, magnitude of x prime dt. In other words, stretching factor times dt. You buy it? It kind of convenient. In some sense, we got super lucky here. We already had this idea of a parameterization. It was just what we needed, and we already knew the stretching factor. We just had to kind of phrase it as such to realize that we already knew what that was. So we're in business, and we'll do an example in just a moment. There's one little point that I want to address first about this computational formula here. You want to compute some scalar line integral. We're going to use this expression here on the right. The problem being that depends on the parameterization. You can see it right here. The parameterization, how you parameterize your curve, shows up twice in there. X as a function of t is a choice. You make that up. That's not given to you in the statement of the question typically. It's something that you pull out of a hat, right? And there are lots of parameterizations. So a very significant worry that we should at least kind of acknowledge is if he picks one parameterization and I pick a different parameterization for the same curve. Well, we're going to be computing totally different integrals. What if we get different answers? Who's right? Right? It's a nasty little worry. So here's the good news. This expression here, this way that we compute scalar line integrals is completely independent of the parameterization. Parameterize however you like. You'll always get the same answer. It doesn't matter. So use whatever's the most convenient. So anyway, I think that needs to get said. The punchline is nothing to worry about. Okay, so now let's do one. Let's crank one out. I'm going to entertain that we have a wire. Mass is distributed across this wire, so it's a non-constant density. Y'all remember questions kind of like this in single variable, mass of a one-dimensional rod. Here the rod's just bent. Right? And we have a indication that this follows a certain curve. The curve is parameterized. By the way, that's not typical. You can't expect that the parameterization will be given to you. Right here, I just want to kind of get the ball rolling. Right? And then the way the mass is distributed is right there. Okay, so with all of that given, let's compute the mass. And by the way, let's also compute the location of the center of mass. And by the way, let's also compute the moment of inertia, specifically around the x-axis. Various different questions that we can ask about this wire. All right. Well, in anticipation of using this formula to compute, what we expect is going to be a scalar line integral, we're going to need to know the stretching factor. To get the stretching factor, we're going to need to know the velocity. To get the velocity, we're going to need to have a parameterization. So let's start with the parameterization and take it from there. Now again, lucky break, won't always be the case, but we were given the parameterization. Sweet. The velocity, you just take the derivative. The stretching factor comes from taking the magnitude of that velocity because it's just the speed. So there you go. This is going to be our stretching factor for all, but by the way, notice all three of these questions, all of these various integrals that we need to compute, same stretching factor because, well, same parameterization because same curve because we're looking at the same wire. All right, and then we just kind of write stuff down. I'm going to focus on this first calculation here. I'm going to focus on computing the mass. My little superstition's not quite the right word, habit maybe. I just like to write down something as a double check here that I'm going to compute mass as the whole being the sum of the parts. Right? That's literally what this says. The whole is the sum of the parts. And mass works like that very conveniently. A lot of other things work like that, so that's nice. On each little piece, mass is density times size. Sure. From the previous page, ds is stretching factor times dt. Ooh, lucky break. We've already computed the stretching factor. So we put that in there like that. Notice we're just plugging in. Everybody happy? Okay, the last little bit, and a constant source of confusion, and you've heard me say this a million times, and again, I hope the more I say it, the less it'll be an issue. How do we figure out what stuff like x is? How do I plug in? How do I pull back the variables in the target? Well, just remember, that's what your parameterization tells you. So in particular, this first coordinate of my parameterization is literally telling me the formula for x. X is t, and so this x here I replace with t. And likewise, the formula is telling me here that that is y. Y is t squared. So this y, t squared. Yeah.
So let's say we have to put the parameterization on our own.
Yeah.
Can it be? I mean, we'd be given more information, right?
Yeah. I'd have to.
Okay.
Yeah, I'd have to give you something to go on. Yeah, absolutely. Yeah.
So to clarify, like if the density was asking for like x cubed plus y, would it be like t cubed plus t squared instead?
Yep. Totally. Exact. And there's well, yeah. Let me just say yes. Okay. Everybody's happy. Okay. Right. Now, let's consider now how to find moment of inertia, and I'm going to make the same sort of starting point. We have a pat formula for moment of inertia. It's integral r squared dm. Remember, there's a bunch of particulars. Don't forget, you've got to tailor that to your circumstance. The r has to be computed as the distance to the axis of rotation. You've got to think through those details, right? But that's a section 5.6 thing. So the more interesting part is what do we do with this integral? And I want you to notice how much of this is familiar. Mass is density times size, just like the previous example we did. Size is stretching factor times dt, just like the previous example we did. The stretching factor, again, same as in the previous example, because that stretching factor comes from the same velocity, which came from the same parameterization, which came from the same curve, because we're talking about the same wire. So a lot of that, again, we get to reuse for free. Okay. And then, of course, don't forget to plug in the variables. And here, for this example, r ends up being y. Now that's chapter 5, little detail. Make sure to think that through. Make sure you're clear on why r is y in this case. But then, how do I plug in for y? Well, y is t squared, as previously noted, and x is t, as previously noted, and all of that comes from the parameterization. Okay. All righty. And let's see here. I will hit that button there. There we go. So I would encourage you all to look through these other two calculations here, the two different coordinates of the center of mass. They're highly analogous. They're going to reuse a lot of the same sort of setup work that we've already done. They're different integrals, of course, because we're computing different things, but look through and make sure you follow all those details. Come to office hours, of course, if you have any questions. It's pretty similar. Here's a different one. I like this example. I don't know. I like the unexpected, out of nowhere aspect of this. So we have a unit circle, and this is like the perimeter of our let's say our property. Maybe I own this plot of land, and for whatever reason it's round. I don't know why. Let's just say, right? And on top of that property line, we've got a fence, and you can think of that fence as being made up of a bunch of pickets, something like that. Now, what's weird about this fence is that the formula for the height is not a constant. Now, I know that's weird, but again, I'm making an example, right? Just something to compute here. Here, the height of the fence depends on where you're looking on the fence. And in particular, the height depends on the x-coordinate by way of this formula. Now, why would you have such a thing? Maybe on one side of your lot you want more shade, maybe closer to where your house is, shade and privacy, perhaps, right? Whereas way over on the other side of your property, maybe you don't want shade. Maybe you've got a vegetable garden. You don't want shade, they want sun, right? So lower fence over there. Okay, so with that set up, how am I going to compute the area of the fence? And again, I start with my my little sort of seeming little triviality. This is an acknowledgement that the total area of the fence is the sum of the areas of the pickets. Physical appeal, right? Just got to think it through, but that's right. That's how area works. That's how a fence works, right? And then we can think about how to compute the area of that, let's call it a picket. And I'm going to recognize that that is, of course, height, which we have a formula for, times the length of that, you might call it the width of that picket, which is ds, because that represents a little piece of my curve that is the property line. And so that being the area, what I have then altogether is that grand total of the area is that scalar line integral right there. Everybody see how I put together that scalar line integral? Right, so it's a sort of a step-by-step thing. It's not because this is some pat formula that that you always use. No. It's because I can make an explicit first principles argument about the quantity in question is an accumulating quantity, and then on each little piece I can just look and see what that little piece looks like and write down the formula for it. And we end up with a scalar line integral just because that's how this one happens to work out. Okay. All right, so how do we compute scalar line integrals? Well, again, step one, we parameterize. And our domain, our curve here, being the unit circle, that's how we parameterize. Flashbacks to chapter 1, right? Remember way back, we talked about different ways to parameterize curves. This was our very first parameterization. By the way, this is a good time for me to remind y'all, you do have to very often come up with your own parametric curves, and it's not always going to be a freebie, right? Something that you've already seen before. So don't forget about our various tricks and tips and tools for how to parameterize things. We've got the graph parameterization. We've got vector algebra arguments and adapting things we've already seen and various other little tricks. Okay, so make sure you're good with all that stuff. And as usual, we take the derivative and then take the magnitude to get our stretching factor. Our stretching factor ends up being 1. How nice. We won't always get that lucky. And then height was given to be that formula. ds is speed times dt. The speed we just computed is 1. Right, I'm just plugging in. Is everybody on board with all that? Okay. Let's see here. By the way, 0 to 2 pi, because in fact this parameterization, we go all the way around because we want the whole unit circle. So this, 0 to 2 pi. And then there's this last little matter of what do I do about the x here? How do you pull back the x? Again, don't forget that's encoded in the parameterization. The parameterization here specifically tells you position in the xy plane as functions of t. In other words, it explicitly gives you x as a function of t, and so x is cosine t. And we've got ourselves a single variable integral and plug and chug, and by the way, make sure you can do that and get the right answer. Okay. Everybody happy? All right. Okay, so let's go with optimism now into this next example. Hopeful that this will work out. By the way, it's not. Something strange is going to happen. Oh, yeah, question?
Yeah, just a quick question about the parameterization.
Yeah.
You just showed that before.
Oh, yeah. Yeah, conveniently, for scalar line integrals, any parameterization is good as any other.
Okay.
Yeah, so it doesn't matter. Right. Exactly. Okay, so here we go. The question at hand, we want to compute the amount of work that it takes to move along this path while exerting forces indicated by this vector field like that. Now I'll explain what's weird about this. The formula that I have circled doesn't work. No pun intended. This formula up here for computing work assumes a couple of things. This assumes that the force is constant over the entire displacement, which you can see right here. It very clearly isn't, right? So that doesn't work. Again, with the, I'm sorry, didn't mean the pun. Likewise, this formula up here in purple assumes that you are moving over a straight path, which we're not. It just isn't a straight path. Maybe we're driving up some mountain road here. It's not straight. So again, that purple formula doesn't apply. Okay, so like we do with every other question of these sorts, we chop it up into little pieces. We look at one little piece at a time, and on any given little piece, any given individual piece, I mean, look at that little piece right there. It's not exactly straight, but it's pretty close. It's very small, and so the vector field doesn't have very much time to move. It can't change very much because all these points are so close together. So my piece is approximately straight. The force is approximately constant. And so on that little piece, I can use this formula, and then I'm just going to add up over all the pieces. Now, so far, I hope this is looking like, it's encouraging that this might actually turn into a scalar line. Right? We're taking a curve, we're chopping it up into little pieces, on each which is easy, blah, blah. Details to be worked out, yeah.
Could you please repeat the justification for the force being almost constant?
Yeah, so I'm assuming that our vector field is continuous, and when something's continuous, when you move not very far away, the thing doesn't change very much.
Okay.
That's all.
It's
Yeah.
the force between vector field and
Yeah, that's right. Okay, here's the first evidence that we have a problem. This is a mountain road. We've been asked to compute how much work it takes to drive up the mountain road. That's very different from the amount of work that it takes to drive down the mountain road, right? You don't burn any gas going downhill. You burn a lot of gas going uphill, not very much going downhill. That make sense to everybody? In fact, it's more extreme than this. Y'all are probably more aware than I about the details of electronic braking. Have y'all heard of electronic braking? It's a pretty cool thing. So this applies to hybrids and electrics. They have coils and magnets inside of the wheels, right? And there's a trick of electromagnetism that y'all will, I'm sure, learn in some E&M class or engineering course or something, where the movement of magnets in the presence of a coil of electric wire will create an electrical current, and you can hook that up to the car battery, and it will charge your battery. Now, this is at the cost of slowing down the rotation of the wheel. Good. We wanted to slow down the rotation of the wheel. We're going downhill. We're trying to slow down. It's a match made in heaven. It's just absolutely perfect, right? So when you apply electronic brakes, as you go downhill, you are very literally recharging your battery as you ride the brake downhill. Does that make sense to everybody? It's really cute, right? It's a really clever little engineering design. Neato. So going uphill is going to obviously cost us a positive amount of work. We're going to exert, and we're going to lose energy by exerting a positive amount of work. If you go downhill, you will exert negative work. You won't lose energy, you will gain energy. So this is very different from anything that we've seen previously. Let me go back to the fence example. If I'm interested in painting my fence and it takes me 3.5 buckets of paint, if I turn around and paint in the opposite direction, will it cost me negative paint? That's nonsense. Not even close. This is silly. Right, completely ridiculous. If I add up the mass of this wire by counting it backwards, will I get negative mass? No, come on, nonsense. Right? None of the examples that we've seen previously have this issue of opposite direction means opposite answer. This is new and weird, right? So the way we address this is we recognize that which direction we go affects the answer. Which direction we go needs to be indicated as part of the question. And in fact, we don't even talk about, in a situation like this, moving along a curve. We talk about moving along an oriented curve. The direction is part of what's going to be the domain for our eventual integral here. It's not a curve, it's an oriented curve. Does everybody see what I'm talking about there? Okay. All right, so I'm going to be on the lookout for that. Yeah.
So you can think of it as like a bunch of like vectors like sewn together.
Kind of. Sure.
You take in magnitude and direction.
Yeah, that's right. Absolutely. So it's like, well, first thing we're going to do is we're going to do that, and then we're going to do this, and then we're going to go like that. Yeah, totally. Yep, totally. All right, so on any little piece of curve, so for example, if we look on this little piece of curve right there, one of our many little pieces of curve that we break this up into, well, of course, on that little piece of curve, we can talk about our displacement. Y'all may recall from chapter 3, we talk about our linear estimate of displacement as being the dx vector. And as we displace accordingly along our little piece of curve, we're exerting a force, F. Again, not exactly constant, but close enough. Goes away in the limit. And grand total, the amount of work on that one little piece of the curve is just force dot displacement. So nice easy formula for nice easy formula for how to compute the amount of work it takes on that little piece. And of course we add up over all those pieces. The total amount of work is the sum of these little pieces of work, and grand total, our work is expressed with this brand new looking expression right here. And doesn't that look different? Right? That really does not look like a scalar line integral. This looks, it just does, straight up doesn't look like a scalar line integral at all. It's a totally different critter. Now, that said, we're adding up over a curve. So it's still a line integral of sorts. Excuse me, but our integrand is a vector. Our differential is a vector. That's creepy, right? First time for us. We've never seen an integral with a vector differential before. That should be unsettling for you a little bit, right? And we'll worry about how do we actually compute with this? Yeah, we'll get to that, right? But those being vectors are why we call this now a vector line integral instead of a scalar line integral. It's just to acknowledge that it's a line integral. Yeah, we're adding up over a curve. Yeah, sure. But in a very different way. Is everybody happy? Okay. By the way, students ask me sometimes, how do you know when to use a vector line integral and when to use a scalar line integral? And the answer is you don't. You don't get to decide. You do what the formulas make you do, right? Why did I write this down? Well, because I had to. Because that's how work is computed. Work is literally a dot product of these two vectors. I didn't choose this. I observed this, right? It's not up to me. So write things down as the circumstance requires, and you compute what you get. It's not a decision. I hope that makes sense? Yeah. Okay. All right, so weird new concept, new kind of a construction. Reminder, it's important to know where these things come from because that's how you're going to solve problems in the future. Right? When you solve problems in the future, it's because you write them down based on the circumstance. But having written such a thing down, now we do need to know how to compute it, and how do we compute it comes from a lot of plug and chug based on stuff we already know. Everything I have circled in purple there is stuff we already know. A lot of this is flashback to chapter 3, I want to say section 3.2. And we defined there this idea of the position differential, dx. And we defined there this idea of the unit tangent vector, capital T, right? Both of which relate to this old idea of a velocity vector, x prime, right? So all of these things are related. More detailed discussion back in chapter 3. You can look back in the notes, look back in the recordings. And in particular, the dx vector can be related to those other vectors like so. Again, all that is old formulas. And so our vector line integral, if you think about it, dx, I can rewrite dx like that or like that, and that gives me new alternative ways to write or think about vector line integrals. So these different formulas, they all have their purpose. Again, they're all just, you just take these existing formulas and plug in for dx, so there's no tricky curves on where these come from, right? But they serve different purposes. Let's talk about the purposes that these serve. This one is, I'm going to say, kind of my favorite. I find this to be very transparent. Somebody asks you a question about some actual scenario, and like this work computation up here, and notice the force vector is very naturally part of the circumstance that I was asked about. I like being able to see that in the notation, right? The dx vector represents my displacement along each little piece of curve. I like being able to see that in the notation. I feel like it's very immediately satisfying when you write down this vector line integral like this. It's really very natural in that way. So that's nice. I like this one for a totally different reason. I like this one because it's already been pulled back. Look at this. It's an integral on the t-axis with a domain given from a to b. So some interval from a to b. This is a single variable calculus plug and chug. That's handy, right? When it comes time to actually turning the crank and computing one of these things, boom. Make sure you know this formula, for sure. Right? Everybody see the appeal? Right? It's clearly a useful thing. This one here has its moments, I guess. I don't really like this notation as much. My main complaint about this notation is in how it makes what we've already agreed is a fundamentally different construction, namely vector line integral, definitely a different thing from a scalar line integral. But it makes it look like it's a scalar line integral. It's got, integral curve ds. It looks like a scalar line integral. Just as a broad stroke, when you have two things that are truly different, you want them to look different in the notation, right? That's otherwise a potential for confusion. That's almost a definition of confusion, right? Where you have two things looking too much like each other, and then you might accidentally conflate one with the other. So I find this notation to be dangerous from a confusion point of view. So all else being equal, not really a fan. Now that said, it's a very popular notation. It's out there. And by the way, it's totally right. There's nothing wrong with this, right? It just gives me the willies a little bit. And so you're going to see this in many books, many other classes probably. Not so much in my class for that reason. All right. Okay, so let's do one. We're going to compute work. It says right there, right? How much work? We have a force given. We have a path given, top half of the unit circle, right? And so this is a question that's seemingly tailor-made for the construction that we just created, right? Force, path, compute the work. That's just what we did. And we're going to start off pretty much by writing down exactly that. It's just that there is this one little sticky, annoying issue, and that is there are actually two forces involved here, not just one. So just as by way of explanations, let's look at this pen right here, right? It's not accelerating. In total, there's no force. But in actuality, there's two forces acting on the pen, right? Gravity is pulling down, I am pushing up. So those two forces are exact negatives of each other. Okay, well, which one of these is the force? Is it this one or is it that one? You got to decide. And you can't just pick one arbitrarily because they're different. They're negatives of each other. So you got to identify correctly what is the force in question. So in this case that we're looking at here, notice it says this is the force that the wind exerts on you. Which one do I need? Well, wait a second here. I have been asked to compute how much work do you exert. And if you want to know how much work you exert, you have to use the force that you are pushing with, not the force that the wind is pushing on you. Does everybody see how those are opposites of each other? Right? So it's a little bit annoying, but the force that you push with is minus F, and that is the negative of the force that the wind pushes with that you are opposing. Right? And this minus sign again is because you're opposing the wind. Yeah.
How do you know you're opposing the wind?
Because if you don't oppose the wind, you'll fall over. Right?
Okay.
So that's right. So I mean, the whole situation here is I'm having to, right? I'm doing my best. I'm walking. I'm trying. The wind is blowing in my face, right? And I'm trying my best to make it that way, right? And I'm having to push that way. And if I were to just stand here, the wind would just blow me right over, right? Does that make sense?
Yeah.
Yeah. Everybody on board? Okay, so this is a little annoying little physics thing that, it's a necessary evil, we just have to say. And by the way, I'm sorry to report there is no sort of like semantical rule that will always guide you in the right direction on this. You have to look at every question that you see and interpret which force were you given, and interpret which force do you need based on which work are you trying to compute, right? And then just look and see, well, was I given the one that I need or was I given the negative, of what I need, and you just got to interpret and and make the decision appropriately from that. So sometimes there's a minus sign, sometimes there's not. Okay. All right, that said, we have our integral written down. We know we need to parameterize and work for there, so I'm going to parameterize like so, because it says right here we're looking at the unit circle. This is how you parameterize the unit circle. Top half specifically is why I only go from 0 to pi, right? And by the way, I am going to deliberately commit a little math crime here. For dramatic purposes, I'm going to ignore something that, in fact, I shouldn't ignore. Feel free to try to catch me on it. I hope you do. But I will come back and confess in just a couple of minutes. But for the moment, we got a curve. We parameterized it. We take the derivative. That's what we need to compute this, right? We're going to need the derivative right there. And now we're in business and ready to compute. And here we go. Let's see here. The f, we were explicitly given to be that. Don't forget your minus sign, recognizing that the f that we were given is not the f that we actually wanted. We've got to keep that in there. Dx is x prime dt. Right? X prime we just computed right there. There is the little nasty business of how do we get rid of the x's and y's. Again, don't forget. Oh, whoopsie, wrong colors. X and y are given in the parameterization. So this x right there is cosine t. And y, again, given in the parameterization. So this y right there is sine t. Is everybody happy? By the way, heads up, you got to watch out. See how there's a bunch of minus signs involved? It's easy to lose track of your minus signs. Do be careful. I try to be as methodical as I can about it. Don't take too many giant leaps of algebra, because that's how you accidentally lose minus signs and get wrong answers. So anyway. Yeah, integral works out very nicely. Pi is the answer. How we doing? Everybody happy so far? Okay. Let's ask the same question we asked previously. Does the parameterization matter? Remember, for scalar line integrals, yeah, it doesn't matter. Parameterize however you like. Go crazy. Whatever. It's all good. Whatever's the most convenient parameterization, fine. Not so for vector line integrals. For vector line integrals, remember, we're not parameterizing a curve. We're parameterizing an oriented curve. Your parameterization has to go the same direction as the oriented curve. Otherwise, you're going backwards. Is everybody good? And why don't I go ahead and do my confession now? This is what I kind of blew on this. I just looked at the unoriented part of the curve, just top half of the unit circled, no discussion of orientation. That's what I parameterized, and I just kind of went on as if that's okay. I gave no consideration to whether I parameterized in the correct direction. And I was given a very explicit instruction that we are going counterclockwise. Specifically, I'd better make sure that my parameterization is indeed going counterclockwise, or I'm just straight up wrong. Does everybody see what I, again, blew past on purpose? And now that's, again, totally not cool. Okay. Now, how do I know? Now, okay, this one, yeah, sure, we're very familiar with this curve. Sure, we know what's going on here, right? How would you know in general if you're not previously familiar with the curve? I'll make this observation that you can look at your derivative, right, which is easy to compute, and then you can take some point. Let's take t equals 0, for example. At t equals 0, My location is here per my parameterization. My velocity vector, here's a formula for it. I can just plug in t equals 0, the same t that gave me this point, see what my velocity vector is. It ends up being straight up. And that shows you that you are indeed, we guessed right here, we got lucky. We are indeed going counterclockwise around that curve. Yeah?
Let's say in another scenario it wasn't like a circle. Would you just have to plug in and then see where it goes?
Yeah, and the geometry is going to be different every time, and like the language that we use to describe which direction we're going is going to have to always be tailored to that particular curve. So yeah, it's another one of these things where you have to take what's given, interpret appropriately, and then take what you compute to compare and just compare that with what you've interpreted from the given. And it's going to be a little bit different every time. Yeah.
If it points in the wrong direction, would you just negate it?
Yeah, no, that's a good question. That's what I was going to get to next here. What if you parameterize the wrong way? And, well, if you parameterize the wrong way, then on each little piece of curve where you were supposed to do this, you're doing that instead. And as you've just pointed out, that means your dx is the exact negative of what it should have been. That means every term in your summation is exactly the negative of what it should have been. And that means that your answer is going to be exactly the negative of what it should have been. Just like you said. Yeah. Right. Yeah.
Yeah, sorry, but could you please repeat how you know?
How what now?
How you ascertain that you're in the right direction?
Well, yeah, so I mean, just in this particular case, I look at the velocity vector and I just see that the velocity vector is pointing in the direction that I think we would have to call counterclockwise, which is what I'm supposed to do. So you just literally compute the velocity, draw that velocity at a given point, and just look and see. Yeah, and it's a geometric, in this case, purely geometric appeal. Yeah. Right. Okay. So now just to document what we just said, I'm going to use the book's notation for this. We're going to introduce this idea of a superscript with a minus sign, and all that does is indicate same curve as C, but going backwards. Same curve, opposite orientation. And the observation we just made is that when you do that, if you go backwards, you'll get the exact negative of what you should have gotten. Is that cool? Okay, now let me say this same thing, right? So again, same notation. If you go the opposite direction, you're going to get a wrong answer by a factor of minus sign. Let me say this a little bit more sort of glass half full. If you need, for whatever reason, to go in a direction that's the opposite of what might be much more convenient, you can compute that integral just fine by going in the direction that's more convenient, and then just don't forget to insert the minus sign to fix your orientation. You can deliberately do it wrong and then fix it by recognizing that having gone in the wrong direction just introduces a minus sign. So you don't think of this as a documentation of how wrong you are. Think of this as an opportunity to turn what might be an annoying backwards orientation situation into something that's oriented however is most convenient. Okay. So that's a nice little trick. I'm going to show you an example of this. I'm actually going to show you, this is actually 4 examples. Another 4. Let's do it like this. So, suppose we want to look at the same top half of the unit circle. This time, though, going clockwise, not counterclockwise. I'm going to show you 2 different ways to parameterize clockwise. And you can plug and chug, just directly take these parameterizations that go clockwise and just use all the same formulas that we just did. Or, if you want, and this is actually the easier way to do it, you can just say, look, you want me to do it, wrong color, sorry. You want me to do it clockwise, you say. Well, golly, clockwise is sort of the opposite of counterclockwise, and I already know how to do it counterclockwise. We just got through computing it counterclockwise. And what I want then is the negative of counterclockwise, and so it's negative pi. Right? So really easy to take, if you need to go in the opposite orientation, just recognize, okay, opposite orientation is going to introduce a minus sign. Just stick in your minus sign, and you're in business. Is that cool? Okay. So that said, I do want to show you how to parameterize clockwise. These are good techniques for parameterizing things. Sometimes you have to actually do it in one of these ways. These are good tools for your toolbox, but we're out of time right now, so I will pick up here next time, and see y'all later. Have a good one. Don't forget about attendance if you came in after. Okay, just a second here.